In the early 2020s, the artificial intelligence industry focused on building digital giants. Researchers poured immense resources into constructing massive models that were imposing in scale but relatively starved for information. The strategy guiding this construction was a set of observations published in 2020, known as the Kaplan scaling laws. These laws provided a specific mathematical ratio for scaling large language models. They concluded that if you increased your compute budget by a factor of 10, you should increase the model's parameter count by 10 to the power of 0.73, but only increase the training data by 10 to the power of 0.27. This equation justified a sprint to build models with hundreds of billions of parameters. Sourcing vast amounts of distinct training data was treated as a secondary concern. We saw this manifest in flagship projects like DeepMind's Gopher, sitting at 280 billion parameters, and Megatron Turing NLG at 530 billion parameters. Both were trained on roughly 300 billion text tokens. Organizations were spending millions of dollars on compute to generate immense theoretical network capacity, but they lacked the volume of distinct examples needed for the network to actually learn how to use it. While the Kaplan laws were derived from empirical testing, a variable involving the learning rate schedule went unaddressed in those early experiments. Early researchers used static learning rate decay schedules that remained fixed even when testing larger datasets. This chart shows a cosine decay schedule, dropping the learning rate to 0 precisely at the final token, 300 billion. When teams added more data, they didn't stretch this curve. The rate dropped prematurely, capping performance and making new data appear less effective. This technical oversight suggested that adding more data yielded diminishing returns, leading the industry to favor model size over dataset volume. In 2022, a team at DeepMind, led by Hoffmann, published the Chinchilla paper to address these scaling inconsistencies. To ensure their results weren't skewed by a single experimental artifact, the DeepMind researchers designed 3 distinct empirical tests. In approach 1, they fixed the model size. For a specific parameter count, they trained multiple versions, varying the volume of training data from a few billion tokens up to hundreds of billions. Crucially, they adjusted the learning rate decay for every single run to span the full length of the dataset, ensuring the model could continue learning until the final token was processed. By plotting the final validation loss against the total compute budget used for each configuration, they traced a distinct envelope that revealed the lowest possible loss. These fixed-size models reached lower validation losses when trained on data pools far larger than the Kaplan laws predicted. The first test indicated that smaller networks possessed a higher learning capacity than previously assumed. To confirm this, they flipped the variables. Approach 2 utilized isoflop profiling. An isoflop defines a fixed compute budget, for example, 10 to the power of 19 floating-point operations. This creates a mathematical trade-off. If you allocate more of that budget to increasing the model's parameter count, you must decrease the amount of training data you feed it. Under this fixed ceiling, the researchers trained multiple models, shifting the ratio between parameters and data. This graph plots parameter count against validation loss for a fixed budget, forming a parabola. The minimum reveals optimal model size and token count. Running this across multiple budgets shows a clear linear upward trend. As budgets grow, optimal model and token counts shift upward. Isoflop profiling established a mathematical framework for efficiency, providing a specific mapping between processing budget and the ideal model configuration. The third test analyzed the data from over 400 training runs to fit a continuous, predictive mathematical function. This equation calculates final loss through 3 factors: textual entropy and penalties for limited parameters and data. Scaling is driven by the denominator's coefficients, alpha for parameters and beta for data. DeepMind's data showed alpha approximately equals beta, both sitting near 0.5. This finding indicates that parameters and training tokens scale with nearly equal weight relative to compute. This is the 1-to-1 scaling rule. If you double your compute budget, you should double the model size, and you should also double the training tokens. This corrected the 2020 rules, which had suggested that parameters should scale nearly 3 times faster than data. To make this actionable, DeepMind converted the complex loss function into a heuristic. A compute-optimal language model should be trained on approximately 20 tokens of data for every parameter it possesses. Applying this 20 tokens per parameter rule to previous models highlighted the scale of their undertraining. GPT-3 required 3.5 trillion tokens, 10 times its actual training set. Gopher required 5.6 trillion tokens, a massive deficit in its training. The three convergent approaches provided a consistent blueprint. The industry had built massive architectures without the required data to function efficiently. To test these laws at scale, DeepMind built a new model named Chinchilla. Chinchilla was given the exact same compute budget used to train the 280 billion parameter Gopher model. They redistributed that budget using the 1-to-1 rule. They reduced the parameter count to 70 billion, 1/4 the size of Gopher, and expanded the dataset to 1.4 trillion tokens. The performance evaluation centered on the massive multitask language understanding benchmark, which covers 57 academic subjects. Chinchilla reached an average accuracy of 67.6%, surpassing Gopher's 60%. These gains were consistent across the big bench suite and specific tasks like reading comprehension and code generation. By holding compute constant, Chinchilla demonstrated that a smaller neural network, conditioned on a larger volume of data, can outperform a much larger network that has been undertrained. This evidence shifted the focus toward the economics of the production phase, where inference costs determine whether a model is viable for widespread use. Serving a 70 billion parameter model in a live environment requires significantly less VRAM. While Gopher demanded multiple high-end GPUs just to hold its weights in memory, Chinchilla can fit onto a fraction of that hardware. Furthermore, generating text with an optimally trained 70 billion parameter model requires only 1/4 of the processing power per token compared to Gopher. These findings altered the strategic roadmaps of every major research lab. The race for raw parameter count was replaced by a race for high-quality data. This has led the industry to the data wall. For a future 1 trillion parameter model to be optimally trained, researchers must source approximately 20 trillion tokens of distinct, high-quality human text. The Chinchilla scaling laws replaced heuristic estimates with a blueprint for efficiency, proving capability scales most effectively when network size and data volume are synchronized.